Hello, welcome to the AIM podcast. I'm your host, Shannon. Today, we're very excited to have Professor Jeremy Avigad joining us to talk about AI and maths.
AI may have the answers, but mathematics has the questions. I should start by saying that, AI for mathematics has been around for almost as long as there have been computers. In fact, even people were thinking about algorithms for mathematical reasoning long before there were computers.
Right.
For me, some of the most exciting things that are going on now are at the intersection of the neural and symbolic. Sort of try to get the precision, but get computer support to make it easier and more natural. So the question of what kind of understanding will we get from AI, I think is a really interesting question. I don't know. We should only be interested in AI insofar as it's useful for us. So trying to set things up so that they're really kind of fruitful and synergetic interactions with AI. I have tremendous faith in mathematics. We'll figure it out.
Hello, welcome to the AIM podcast. I'm your host, Shannon. Today, we're very excited to have Professor Jeremy Avigad joining us to talk about AI and maths. Jeremy is a professor of philosophy and mathematical sciences at Carnegie Mellon University. He has been a leading figure at the intersection of AI and maths well before it became the hot topic it is today. He is one of the early forces behind Lean, the proof assistant now central to many efforts connecting mathematicians, AI systems, and formal proofs. He has also been a deep thinker on what it means for AI to be genuinely useful for mathematics. Recently, there have been a lot of exciting updates around AI for mathematics. Just in the past few weeks, an OpenAI model found a counterexample to a nearly 80-year-old conjecture of Erdos in discrete geometry. And fields medalist Timothy Gowers wrote about ChatGPT models finding a useful idea in under 2 hours. As models and agents get better at solving math problems and writing proofs, they also raise deeper questions. Can mathematics be automated? What does it mean to learn and understand maths? And how should mathematicians use these tools? With all these questions in mind, we sat down with Jeremy, and we had a very insightful and inspiring discussion. Hello, Jeremy. We are really thrilled to have you on our podcast. Thank you for being here.
It's a pleasure. I'm delighted to be here.
Yeah, thank you so much. Today we're going to talk something about human-AI collaboration in maths. And then, Jeremy, you have been a leading figure at the intersection between AI and maths. So before we get into the weeds, I was wondering if you can share a bit about the big picture of the landscape of AI and maths.
Yeah, I mean, things are happening at this dizzying pace. It's really hard to keep up. I should start by saying that, AI for mathematics has been around for almost as long as there have been computers. In fact, even people were thinking about algorithms for mathematical reasoning long before there were computers.
Right.
In the AI landscape, as you know, there are these two traditions. There's the symbolic tradition, and there's the machine learning. I think, historically, mathematical reasoning has been aligned with the symbolic tradition of being very precise, very rule-based. Mathematical language has a very precise grammar. There are very precise rules of inference. In the latter half of the 20th century, it was really symbolic methods that when people thought about AI, they thought about automated reasoning. But I think we're realizing now that, what I love about mathematics is I think it's actually it's a beautiful combination of the symbolic and the kind of neural. What we love about mathematical reasoning is that on the one hand, it's very precise, but there are these, what we really love about mathematics are the big ideas, the intuitions, the insights. Yeah.
It's coming out of nowhere, right? You cannot explain with...
Well, it's not coming out, it's coming from, but it's coming from somewhere, but it's hard to say where.
Right, exactly.
And it's from our experience, it's from the things we've read, the things we've seen. And those are the things that machine learning is really good at, kind of synthesizing lots of experience.
Right, totally. I'm not sure if I qualify to say this, but I feel intuition is kind of like some sort of advanced heuristics we developed through our experience. But also, it's so evasive, right? We cannot really say this is a formalization of the heuristics. But yeah, this is fantastic. And then also, what do you see in the last few years? I guess there's a speed up with all this like latest
Yeah,
generation
well,
of AI models?
so as you know, I mean, so again, through the 20th century, there were symbolic methods and first-order theorem provers, and there's the SAT solver revolution and striking advances, you know, in being able to solve large combinatorial problems. But it was really, and I mean, even with you know, the emergence. I mean, ChatGPT. What was that? 2022. Yeah. So you know, in the early days of ChatGPT, I mean, it was. We used to make fun of the fact that you would ask a mathematical question and you would get something that looked, you know, like a beautiful mathematical proof, and it was total nonsense. So it's really very recent that that machine learning really has been shown to be able to support mathematical reasoning, but as I said, progress has been very fast. It's been dizzying. So there's been a tremendous, and I think machine learning researchers are realizing that. In a sense, AI for mathematics is the next frontier. It's you know, if you want AI systems to be useful, they have to be correct and they have to be precise. And so trying to figure out how to get that precision, and again, the advances have been stunning.
I think this leads to some of the beautiful nature of maths, because they're just like a mechanism that we want to ensure they are by construct correct. And also, again, goes back to what you're saying just now, which is initially the model can generate like a seemingly correct piece of text. And I think this all goes to this like subtle difference, which is like they also generate this piece of text today, but they're correct, right? Yeah. And then how, like, there's a tremendous effort to transition from one stage to the other, but also like from like a outside appearance, they just like change a bit of lines of text, whatever, right? I think this is kind of like very fascinating over there.
So I think for me, some of the most exciting things that are going on now are at the intersection of the neural and symbolic. So one way systems are getting better at being correct are by interacting with symbolic systems like Lean, where there is a precise standard of correctness, there's a precise measure of correctness, and there's a very strong signal. And that's not the only way. I mean, so people will also, you know, will train natural language verifiers and so on. So there's research on both sides. But I think most people believe that that both approaches are needed.
Yeah, that's a perfect like transition to talk about like the difference between informal and formal mathematics. Would you mind to share a bit of that?
Yeah. Well, I mean, in a sense, formal languages are fairly, in the sense of formal logic, are fairly new and fairly recent. I mean, there were. You know, in the turn of the 20th century, there were the first axiomatic foundations for mathematics. But in a sense, the symbolization of mathematics, I mean, it goes back to Aristotle. Aristotle used, you know, Greek letters to stand for propositions and have the rules of inference. So I think the passage from informal to formal is when you identify, again, you try to identify in very precise ways the grammar and the rules of inference and so on. And so those ideas have been around for a while.
Right. So basically, if I understand correctly, I think like informal is more or less like when you describe a proof, you write in natural language. It's sort of correct, but also you need some sort of like human interpretation to fill in the missing gaps in the middle. And in contrast, like a formal language is more or less like you can turn this into like a precise program that it can run some rule-based checkers to ensure that it's guaranteed to be correct if it's done correctly.
Yeah. But I think that's right. I mean, people always often point to the phase of mechanical checkability. Right? You can mechanize it. I mean, informal mathematical language, it's a funny thing. It's not quite natural language. I mean, it's among the human activities that we do with language. It's very precise, very regimented. And in a way, the formal languages are kind of like an analysis, a codification of what the rules are.
Right. I think maybe this is the right time to ask a bit about like why people started this transition from informal to formal, and then what are the problems people are trying to solve in this direction there.
Yeah, well, I think it goes back to think, you know, well, why do we even have mathematics at all? What's the point of mathematics? And I think mathematics has changed tremendously over the centuries. But I think, you know, there are some things that have remained constant and steady. And, you know, what characterizes something as mathematics is, again, it's the precision. And it's that precision that it's important for communication, right? So, okay, so if you take any other scholarly discipline, right? If I make a scientific claim, you dispute, we can argue and argue and argue about the interpretation of the data and not come to any conclusion.
Yeah.
In mathematics has this amazing ability to bring people together to agreement as to whether something is correct or not.
Yeah,
right?
That's
I mean, a mathematical, and again, this goes back to ancient, you have Euclidean proof. And again, philosophers were always debating over the rules of Euclidean proof and is this obvious and is this justified? But for the most part, in ordinary practice, people could read and write proofs, and they wouldn't get into these fistfights or arguments. Is this correct? Well, you think this. Well, I think that. Well, there's always a way to get to the bottom of it.
Yeah, this is kind of marvelous because there's a so-called reproducibility crisis in machine learning, maybe in other fields as well, which is like you run the experiment, people are like, hey, I cannot reproduce it on my side. But this seems to be not existent for a few.
So the trick is the way mathematics achieves that is by kind of separating the rules from the interpretation.
Right.
So you take a fact like 2 + 2 = 4, right? Well, there are lots of counterexamples. I mean, you take 2 drops of water and you add 2 drops of water and you get a puddle. You have 2 rocks and you bang together, right? But you say no, that's not what I mean, right? So something becomes a piece of mathematics when you sort of fix the rules of use, and then the application is where you interpret it. Oh, well, does it apply in this situation or does it apply not?
Right.
And so. So that's something that's gone back. I mean, I think that's something very fundamental to the way we communicate and reason, this kind of yearning for this stability. And I think that's what makes mathematics special. It gives us a precise language in which we can state results, which then let us interpret the science, interpret our other activities, interpret science, and so on. And so if you accept that that's sort of one central feature of mathematics, that kind of precision.
Which is very beautiful.
Yeah, and so then the symbolization and the formalization is really just kind of an extension of
it's
that.
natural in that direction.
Yeah.
And then maybe it's a good point to talk about like some of your effort in trying to leading the development of tools like Lean and also support like computer-aided proof, etc.
Yeah. So again, I've always thought of. So it's interesting when so those of us who work in formalization, in the early days, you have to be careful. I mean, so people in the field sometimes pitch that, well, we need to formalize mathematics. There are mistakes in mathematics, and if you formalize it, then it gets checked, and then you're sure that it's correct.
Right.
And
it's kind of a stamp.
But most mathematicians kind of reacted kind of negatively. I mean, the attitude was like all this focus on formalization. Their attitudes like when you formalize mathematics, that's when the mathematics dies, right? What we really care about are the ideas, the insights, the intuitions, and so I think you have to be careful. The way I like to think about it is. Certainly what we love about mathematics are the ideas and the insights and the intuitions and the way it sort of lets us make sense of experience. But the precision is the medium. It's the language. It's the. Right. I like to give the example that maybe your favorite sport is soccer and so if I say that. People play soccer, there's a field and there's a net and there's a ball. You might say, no, you're missing the point, right? Soccer, it's all about strategy, it's all about speed, it's endurance, it's about teamwork, and right?
But the foundation is built.
But if you're not kicking a ball, you're not playing soccer.
Yeah, totally.
Right? So, the game, it's the rules of the game are what makes it, it's the precision, I think, is what makes it mathematics, but what we love about it is the ability to build the ideas on top of it.
Right. It's kind of like you have the solid foundations. Then you can talk about this, like, the fun parts of it. Yeah.
So I think those of us who are excited about formalizing mathematics, it's really the formalization as the medium that lets us do the mathematics we want to do and supports us in thinking about mathematical ideas.
Right, totally. And then I guess you were one of the earliest persons to start in doing that, right? Because when I read your profile.
Yeah, I got, I have been, I started experimenting with proof assistants in the late 1990s. With Isabelle on a system that was then called COC. It's now been renamed ROC. But the first system I spent a substantial amount of time was called Isabelle. And one of the earliest projects, sort of my claim to fame in the field, was to formalize the prime number theorem, the Hadamard-Delaunay-Poussin prime number theorem, around 2003, I think, with some students at Carnegie Mellon, some undergraduates, and a graduate student at Carnegie Mellon. And at the time it was just for fun. It was just a thing to do.
It's the best work. It's like you do something for fun, and then suddenly it becomes something so good and so important. Yeah.
And so so that was So I've been doing this for a while.
Yeah, wow. When I read your profile, like I think you shared the history of you started working on this, and then you started working on some other projects about formalization. Then you someday you feel like, should we start building something about a toolkit for the formalization process, and then that magically to Lean. I don't know. Yeah.
Yeah. So the story is, I worked with Isabel after the prime number theorem. I was burned out, and I sort of put it down for a few months. Then I came back and I started breaking up material from that and contributing to the Isabel library. Then a few years after that, Georges Gontier invited me to. I had a sabbatical. 2009, 2010, I had a sabbatical year, and Georges Gontier invited me to come to Paris and work on the formalization of the Feit-Thompson theorem, so another major project that he had developed. And so I spent a sabbatical year in France. It was a wonderful year. I spent the year learning Koch and dependent type theory, learning finite group theory, learning French. Everything was new, everything was different.
I heard learning a different language, kind of reactivates some part of your brain and then get you new inspirations. I don't know if that's true.
Yeah, no, absolutely. No, it was a great way to spend a sabbatical. Again, when you just sort of just do everything different.
Right.
Yeah.
And then the next time you met Leo and other co-contributors.
So I came back from 2010. I returned to the U.S. And again, I said, okay, I'm tired of formalization. It's been fun, but I really want to think about automated reasoning. I was more interested in automation. But a couple of years later, 2012, I went to a meeting. It was the Turing Centennial. It was after the Turing Centennial. There was a meeting at the Isaac Newton Institute in Cambridge, and I went there and I spent time with a friend of mine, Grant Passmore. And we were talking about ways that we could try to get formal methods in the hands of mathematicians, right? And we reasoned as follows. We said that, look, very few mathematicians are using proof assistants like Isabel and Rock and so on. But lots of mathematicians use computer algebra systems. And the reason, because anybody can sit down with a computer algebra system and you write, x plus y to the 100, you hit a button, you see things happen, right? You can interact and play. And so we decided that the way to get mathematicians thinking about these mechanical tools for reasoning would be to add it to a computer algebra system. And so we chose the open source system SAGE. And Grant had just done an internship with Leo at Microsoft. And Grant said, hey, let's get Leo on Skype. It was Skype at the time. And so that was when we started this project to build this symbolic interface, this logical interface to SAGE. So I returned to Carnegie Mellon in the fall of 2012, and we were working on this project. And that was when, I think Leo at the time he had gotten tired of his previous project, Z3, he was looking for a new project. And so it was a few months later that Leo announced that he was going to start the Lean project. And so when he did, we just sort of dropped everything. We all just turned our attention to that.
Wow, that's marvelous. You play with some ideas, and it suddenly just worked out.
Yeah. So, so the exciting thing about it is, even before Leo started Lean, with the SAGE interface, the discussion was, we wanted to implement a logical language that would let people express mathematics, and so all the discussion was, what should the language be, right? What are the mechanisms by which we should express mathematics? And so there was a lot of discussion of different logical and axiomatic foundations. It was very intoxicating, the idea of trying to design the perfect language. And so, the early days were, Leo did all the hard work of actually implementing it, but, I've just hundreds and hundreds of email messages talking about what the language should be and how mathematicians should be able to express their ideas.
Yeah, I totally feel that, because I think there are two ways I can relate. One was when I first discovered Jupyter notebooks instead of set of programs, right? It's Python interpreter has always been the same, right? But I think it's more or less giving people direct, interactive responses to experiment with things, to know what's the outcome of a program, and then that kind of like it's really kind of like the bicycle of your mind, right? And I think I can definitely feel that.
Yeah, I mean, they're called interactive theorem provers,
Right,
and it's really the interactivity.
Yeah,
you know,
yeah,
you do something and you get a response. And
Right.
I think, and what people really love about Lean is the user experiments. You know, you're in the editor, but there's all kinds of information flowing back and forth, and things popping up and clicking on things.
Right.
And it's that interaction that really feels good.
And then I think the other thing is I think there's this pure joy of creating something new from scratch, right? Because you have this like massive design space. It's great that you can working with other people together to do this, and you can debate to feel the right way to design all this.
So it's exactly as you say. The idea of so I think. I mean, Leo is amazing. Leo is one of my heroes, and so to have somebody of that caliber who was excited about this project of starting a new proof assistant was wonderful. Right. But it was the feeling that we were doing something not just interesting, but we knew it was important from the beginning. We knew that this was an important thing to do. But the feeling that. We could decide, it was really just kind of, it's like creating your own world.
Yeah, totally.
It's that freedom.
Right. But also, it's not like your fantasy world. It's kind of like rooted in this mathematical, in the logic and reasoning. And then you are getting closer to some
the precision somehow feels very transcendent. You build a library, and it's there. I mean, once you check something formally, it's there forever. Right? It's in the cloud digitally. It's it's this artifact.
Right. And now I see this like reasonable next step, right? Because if you think about the root of maths, you definitely want to pursue something about precision. Yeah. And when you have something about precision, then your next step is reasonably think about like how to automate some sort of reasoning steps.
That's right.
And then that actually leads to some of your recent work in collaboration with computer scientists about like improver and also maybe lean architect. I don't know if you want to share.
Yeah, no, I'm happy to talk about that. So the downside of interactive theorem proving is that the interaction is often means that users have to do a lot of work. And so even from the early days in the prime number theorem with Isabel, again, I was very much taken by the idea that if this is going to work, we need better automated support, that the computer really has to help us more.
In that, like, people spend meaningful time interacting with this.
That's right. You spend way too much time, ordinarily just working through low-level inferences, and you have to sort of memorize the name of hundreds, thousands of facts in your library to apply this one, apply that one. And so I think from the beginning, the emphasis was to sort of try to get the precision, but get computer support to make it easier and more natural. And so this is where machine learning and neural AI is a game changer. It is. So the projects you mentioned. So two recent projects. So it's interesting. Both projects you just mentioned are master's projects. So Improver was the project. It started out as a summer research project by Riaz Ahuja. It was supervised by Sean Wellick and me. So Sean is a colleague at Carnegie Mellon. So Riaz so Carnegie Mellon has a math major, has an accelerated 4-year master's program. So it's very grueling, very demanding. So, but Riaz Ahuja he's just graduated, but he was in that program. So he was very ambitious, and so he was looking for a project. And the thought was, rather than, so this was 2024,
that feels also
ages ago. But the thought was, rather than try to write proofs ab initio, we set him the task of, given a formal proof, can you improve it? Can you rewrite it? And so he experimented with just off-the-shelf foundation models to develop ways of improving them. And there were questions of not just prompting the models, but what kind of information, what kind of context. And so the first paper he actually done pretty quickly. He got a system that did reasonably well. Then the next challenge was, so the problem is, of course, using a foundation model is expensive, and if you want it for testing and so on. And so the second challenge we set to him was to see that if he could decrease the cost and get by with with a weaker model.
Yeah, open source model.
With an open source model, and then with training, and so that was the next version, and he managed to do that. So he managed to approach the performance of the stronger models, but using the weaker ones with
proper post training.
With post training, well, there are a lot of ideas in the paper. I mean, another one that Sean's group has really kind of developed and honed is what we call neurosymbolic augmentation. Right. So it's a model of what information are you exposing to the model to learn, and so things like in the context of working through a proof, I mean, Lean gives you a lot of information about the state, the context, the hypothesis, and so it's trying to figure out both at the training time and inference time, just trying to expose the information that will help the models learn better.
Right, and then I can imagine that's like before the agent time, right? Because that time was like people still need to decide like what information to be fed to the models.
Yeah.
But then I think nowadays the trend is like, you know what? We just build everything, throw these two agents, and then they just run this like long form IL in their environment.
But I think so. I think so. At his master's defense a few weeks ago, we asked about this, and he pointed out that, so what I think the key advance of that work is showing how you can kind of distill the performance into weaker models. And then it'll scale up. I mean, you can then put in an agent. Now the agents will do better, with less compute. And the other project you mentioned, Lean Architect. So let me go back. So in the formal methods community, so you mentioned that one of the things that formal methods is good for is collaboration. Right. And this goes back to about 2021. Patrick Massot wrote a tool called Lean Blueprint. Which was a way that people could collaborate on a big formalization project. So it was first put to use to great effect in the liquid tensor experiment, the challenge posed by Peter Schulze. The methodology was that the person leading the project would arrange to have a LaTeX blueprint, a very detailed presentation of the proof. And then you set up the Lean repository and you coordinate.
Yeah, they intertwine each other.
Exactly, right. And so you have the formal and the info, and then you have web page and tracking dependence, and it's easy to see where you are and to get the dependency graphs and see where you are in the project. Okay, so that's background. So there's this wonderful collaborative software called Lean Blueprint. So Thomas Xu was a master student with me and Sean. So he did work, with another student of mine, Josh Kloon, we had worked on developing a sledgehammer for Lean, and Thomas took the lead on developing a neural method for premise selection. So he did that project. He did other projects as well. He's also developed with Sean's group Mini CTX, which is sort of a bench. So the problem is, you can train. People will typically train neural provers on MATLAB, on the math library. But you have to remember that ordinarily people will then be working in the context of their own project with the prover. And so we wanted to have benchmarks that would measure how well provers do in a new context in a project.
Like adaptation to specific new project.
So Thomas did the premise selection, Mini CTX. He went off to the summer. He went to ByteDance and he worked on Seed Prover. And he came back, all energized by that experience. But he had a semester left, and he said, "Well, what do you want to work on?" And he actually pitched this idea of Lean Architect. And to our surprise, this was a symbolic system. This wasn't a machine learning project. So what Lean Architect is, it's an augmentation. It builds on Lean Blueprint. So the problem with Lean Blueprint is that you have to develop the LaTeX. Mathematicians have to develop the LaTeX. They have to develop the Lean files, and then they have to synchronize them by hand. Thomas's idea was to basically combine them, so have ways of putting your LaTeX into the Lean documents and adding your annotations to the Lean files, so that the dependencies are tracked automatically. It would generate then the whole structure. And there were two motivations for that. One was that this would be better for the human users, because they wouldn't have to go back and forth between the two. You have one system, right? But the thought is that it would also be better for AI, right? Because they are in one uniform place. You have the informal and the formal together, and the dependencies and all the information there.
Makes them easier to get the context correct.
Yeah.
Because otherwise they have to do all the grips for other files.
Exactly. It kind of it's kind of setting it up.
Yeah.
It's setting up the context.
Right. But also, you want to design the system also kind of friendly to users, such that this will be this kind of like organic human AI collaboration happening there, in that people can use it, agent can use it, and then they can bootstrap more on the user data as well, which is kind of like, I don't know who we are working for now. Are we working for us, or are we working for agents?
Well, no. So yeah. No. I really like this perspective because. We should only be interested in AI insofar as it's useful for us. So trying to set things up so that they're really kind of fruitful and synergetic interactions with AI, I think is the way to go.
Yeah, totally. I have one more question on this topic, which is like, as the majority of our audience perhaps is like computer science, backgrounds. Do you have any suggestions or thoughts about like how, for those who might be interested in getting in this domain, any high-level guidance or like tricks to work, and maybe what a specific problem to focus on? Yeah.
So, it's interesting. Early in my career, being a mathematician was, I went to work, I would sit at my desk and write a piece of paper. And so the idea of now having students and interacting with people, it's kind of new in my career. I enjoy it very much. What I like about logic is that it's between mathematics, philosophy, and computer science. It's a place where people can all come together. And so, my one piece of advice to computer scientists is work with mathematicians, get to know mathematicians. And it sounds like it's an easy thing to say, but it's harder than you think to do in practice, because mathematicians and computer scientists talk differently, they think differently, they act differently, they, just everything in terms of the goals and outlooks and perspectives. But I think it's the collaborations, the interactions where really, really interesting things happen. Right. So rather than any kind of technical advice, I would say find some way to collaborate, interact with mathematicians, because you'll just find yourself with just new ideas and new insights and kind of exciting things to do.
Yeah, totally. Like, as we just start talking for 20 minutes, I'm learning a lot, and I do feel like I think it's very unique experience talking to mathematicians, because I think you guys think a ton, and then you care about the logic and reasons behind things.
Yeah, I mean, mathematicians are amazing. I mean, there's this purity to it. I mean, mathematicians don't care about anything other than thinking about mathematics, right?
Yeah,
I mean, I've always that mathematicians, look, we make less money than computer science. We're less, less grant money, less fame, and so. But mathematicians don't care. They're in it because they just the pure love of the subject. And I once gave a talk at IGCAR, and I said to a computer science audience, I said, look, if you collaborate with mathematicians, it might not get you lots of citations, it might not get you lots of grants and so on, but I can promise you that at the end of your career, if you do something useful for mathematics, that at the end of the career, you'll look back on it one day and it'll be among the things that mean the most to you. So.
Wow, that's impressive.
Yeah.
Okay, speaking of your love for maths, maybe we can also talk about how the AI is also changing maths themselves, right? How AI is changing the perspective of mathematicians. And I guess you have a lot to say, because I also learned a lot from your writings.
Yeah, well, so I think the short answer is we don't know. I think it's becoming clear that AI will change mathematics, but we don't know how. I mean, and there's some anxiety, for the better, for the worse. I mean, change is hard, and so it is provoking some anxiety. I mean, I worry that mathematicians aren't taking it seriously enough, in the sense that there's a lot of talk, there's a lot of excitement, and people AI, and at the joint mathematics meetings the year before last, it was the age of AI. So people are aware, and there's a lot, but I don't. In terms of actually just taking action, I worry that maybe, I mean, the mathematics community is very, very conservative. We've been doing mathematics pretty much the same way for centuries, and things change over time. But the standards of what of evaluation, assessment, what counts as good mathematics. Mathematics is so abstract that we tend to look to the views of experts as to what's important and what we should be doing, and we tend to look to tradition. And so it's not something that changes quickly, right? I mean, the kind of mathematical values are very kind of deep rooted. And so, yeah, I mean, we're now at a time when lots of things that we thought that only we could do, and this is, we're mathematicians, we can do this. This is our superpower. We're seeing that some of those things that AI can do better, and possibly better than we can. And so that's, I think, causing us to rethink and reevaluate. Okay, so what does it mean to do mathematics, and what is now the human role?
Yeah. So I'm actually curious. Like, what are the things you see that AI can start to get better?
Well, it's really on both ends. I mean, so again, mathematicians can construct these very long, complicated argument proofs. Can be hundreds of pages long, right. And they're very, very precise. And the pieces I mean, if you have a proof, if there's one lemma wrong, one line right, it falls apart, right? Yeah. And so to be able to construct these very long, complicated chains of reasoning and get it, fit together just right. I mean, that's something that we've taken pride that we can do. But again, we're both seeing both on the informal and the formal that AI is starting to do that. And I think there's no reason to, well, I mean, we are seeing that it is able to construct long formal proofs. And so, yeah, okay. So on the other hand, say, but yes, we have the insight, we have the intuition, we have, the big picture, we can kind of synthesize these ideas. But machine learning is good at synthesizing lots of data and patterns. I mean, where do our insights come from? Well, we've studied, we've read the literature, and we've studied in graduate school. We read all the textbooks and the monographs. But AI has read every Yellow Springer book that we've read. It's read every archive paper that we've read, and many more. And so I see no reason to think that that AI can't make the connections and detect the patterns and notice the connection between this branch of mathematics and that, and come up with suggestions and insights and intuitions. So at both ends, both the low-level detailed and the kind of big picture, I think AI is,
I don't know how to react about it, which is like,
I don't either, right? So,
yeah. Which is, I think there are a bit of like more fundamental questions which we can talk more about, like how do you understand maths or how do we do maths. But I think one positive side of everything here is like we do have the stronger tool that we can leverage to augment us. And I guess you also have this like very optimistic view on AI.
For the most part, I mean, again, I have anxieties. We all have anxieties. I have anxiety. For the most part, I am optimistic. I mean, the technology lets us do things that we could not do before, and that's what mathematics is all about. It's being able to solve harder problems, and so. I do think that this is, for the most part, a technology that will let us do mathematics better and do things that we couldn't do before. And so we just need to figure out how to use it and what we want to do with it. Yeah. But at the end of the day, I mean, it's us decide. It's a technology, and it's a technology that helps us achieve our goals. And so we still need to figure out what our goals are and figure out how to use the technology to achieve them. But it's still our mathematics, right? It's still us doing mathematics.
And that's a great way to summarize this, which is, as you just said there, right? Because I'm literally quoting from your writings, which is like, rather than fight the use of AI in mathematics, we should just own it, right? And I think nobody knows what's the limit. Maybe sky's the limit, I don't know. But also I think there are certain parts of the models and the agents are still far from perfect. And I guess I can definitely tell a few aspects from some of your writing and thoughts. For example, maybe evaluation is a big part, right? Because you wrote about it, saying that the current design benchmark for AI, current benchmark design are coming from AI researchers, and they don't really reflect the real use of these models with mathematicians in practice, right? Maybe you can say a bit about that.
Yeah, so that's. So one thing I'd like to just mention for the record is that when we talk about machine learning for mathematics, it really is a wide variety. It's not any one thing. We've been talking a lot about neurosymbolic theorem proving, writing both informal and formal proofs. But I think we should remember that there are lots of ways that machine learning is being used now. So, for example, people have used machine learning and mathematics in ways of showing it different types of mathematical data and using it to detect patterns and connections between different types of algebraic invariants and so on. And then those become intuitions that become then the contents of ordinary mathematical theorems, right? So it's kind of exploring and detecting patterns. There are machine learning techniques for searching for combinatorial objects and finding interesting combinatorial objects. There are neural techniques for computing solutions to PDEs and exploring the space of solutions and exploring kind of analytic data and so on. And I think there's as much promise in those aspects of the tools as well. I think, I try to remind people that we've seen these very, very striking examples on just the theorem proving side. But, I mean, billions of dollars have been, I mean, this is just what both big tech and lots of startup companies have raised money and put engineers on. And so we've seen very striking advances there. But I think there are other aspects of AI for mathematics in terms of exploring and gaining intuitions. And so now I forgot, what was the question?
Okay, maybe I can summarize this, but I think what you just mentioned, it's sort of like, maybe it's kind of the deep learning era or whatever, which is like you have a very specialized problem. And then people build around machine learning models to solve that specialized problems. But I think moving to this like LM or agent era, I think the shocking difference is like you don't, like people start to just take models out of the box and then just apply this to different kinds of problems. And this is like magical emergent properties or emergent capabilities. And I do agree that I actually think like, advances in this specific direction is very, very important because they are way much more efficient than just like having agents do whatever they want for hours and then we don't know how to verify that. But also like the trend is more or less like, can we also extract more from the current general purpose?
So you would ask me, I think you would ask me about the range of mathematical activities, right? So it's not just about proving theorems. It's about exploring.
Right, exactly. And I think that's actually a perfect answer for the question I asked. You were saying basically we want to play in a more active role in deploying this technology. And then what you said is exactly the case, which is like when people think about evaluations, we should not just focus on the trendy ones, but also focus on like the broader picture of all the different sub-branches in maths, as well as all the different problems people can tackle. And then just think about like how mathematicians can really benefit from that, rather than just think about like, oh, we get like higher benchmark scores.
So here's another way to say it. I mean, so colleagues say to me sometimes, well, why do we need to, have people do research in AI for math? I mean, the tool is just getting easier to use. We just wait and I'll just, ask Gemini to prove my theorems and so on. And I think that's not the vision I'd like to see for mathematics. I'd like to see, mathematicians finding really exciting, insightful, novel, creative ways to use AI. If mathematics just becomes you sit there and ask, ask Gemini questions, I think we're much better than that. We're much smarter and more creative. And I think, and that was the thing about sort of harnessing AI and molding it to. We've got to figure out how to use it and what to do with it.
Yeah, I really love the way you're talking about this because, people always use like a calculator analogy, right? Because we invented calculators. That doesn't mean we don't need to learn math, right? People start to operate at a higher level. And I think the really big question here is like, what's the higher level on top of these agents?
What are we going to do with it?
I think that's really, really fascinating. And I guess that's a very interesting open questions for the audience to think about. Hey, what can you build to enable this? Right. Great. And then the other is perhaps about verification, which is I think there are two separate questions about it. Which is, first of all, is agents or whatever AIs we have today, they can, just like you said, right? They can start to generate seemingly good and correct answers. Then the question is first is like, it's not easy for us to verify that. And actually, when they generate like an 80-page of proof, it takes people maybe more time to verify than just write themselves, right? This is kind of an inherent challenge here we're facing, which is like the easiness of verification of the correctness of the outputs. But there's a deeper problem, which we can talk more later as well, which is even if the agents are being totally correct, sometimes maybe if the trend goes up, keeps up, then we might have some AI that can generate some like proof that maybe it's beyond our capability to understand. Yeah. And then what will happen in that case? But maybe we can talk about the first one and we can gradually move on. Yeah.
Well, let me do the second one first.
Okay, great.
Right. So the issue about kind of proofs that we don't understand, in a way, that question, we've been there before. With the four-color theorem, with the computational proof, right? And initially, when the proof was controversial, it wasn't that mathematicians worried that it wasn't correct. They said, yes, okay, now I believe the theorem is true, but they felt that the proof didn't deliver the kind of understanding that we want.
I remember it was a bunch of computer scientists. They did like a huge amount of search.
It was mathematicians, but using computer search. But what they reduced, there was ordinary mathematical work, a pen and paper reduction, where they took the problem, they reduced it to a combinatorial search, and then it was coding up the combinatorial search, and then you run it. And it's just brute force checking lots and lots of cases. So there is a clever reduction, and then there was brute force enumeration and checking. And it was the brute force enumeration and checking that, like, well, no human could check them all by hand, and so somehow we're not internalizing. And but I think we sort of got past that, right? I think most people believe that for that proof, there really is nothing more. I mean, over the years, people have searched for shorter proofs, maybe survey, but I think sometimes a proof is just a calculation, and we've learned to accept that. I think in the same way, verifying some results. I've written about the fact. I once wrote an essay called "Varieties of Mathematical Understanding," where I point out that the ideas of what it means to understand mathematics have changed over time, and they're constantly changing, and they will change. And so, going forward, I can imagine this notion of understanding why a result is true. Well, maybe from the AI we have a high-level overview, but then there are proofs that are long, technical, lots of cases that AI just, and maybe we care, maybe we don't. But very often understanding is very pragmatic. We want to understand a proof so that we can do the next one, right? So the question is, so a proof tells you, that a theorem is true, but it's very often the case that a theorem is proved and then people just reprove it. They find new proofs. And the reason that we value those new proofs is that they teach us things, right? They give us new types of understanding.
It's a process that matters.
Yeah, exactly. Yeah. And so the question of what do we get from mathematical proofs and what do we get from our mathematical artifacts? Again, understanding is a wonderful word. It's something very complex. So the question of what kind of understanding will we get from AI, I think is a really interesting question. I don't know. But I can imagine it will be different from what we've looked to from journal papers in the past. Yeah, but on the other hand, we still teach children arithmetic.
Yeah, exactly.
So first of all, having a number sense in general is useful, right? You're not always going to pull out a calculator, but also understanding what the numbers mean, what the symbolization means, and so there's certain things that we're willing to offload to machines, but still. There's something that we want to be ours that we need to understand. I think it'll be similar with AI. Totally. Some things will offload, some things will be important to us, and again, I have tremendous faith in mathematics. Right, we'll figure it out. There's something fundamental about the drive to understand, and so we'll figure it out.
Right. I guess that's a perfect segue to talk about this, education and maths perspective. I think which I know you're a big fan of. And I think a lot of we chatted about also kind of corroborates with Timothy Gowers, who mentioned that who is first of all Fields Award winner, and he tried it out GPT 5.5 with combinatoric proof.
And just a few days ago.
Yeah, just a few days ago. And I think I want to quote what he said, but I think that's kind of a good characterization of what we're discussing here, which is a better answer is that by solving hard problems, you get an insight into the problem-solving process itself. Right? And at least in your area of expertise, in a way that you simply don't if all you do is read other people's solutions, right? And I think that kind of justifies the necessity of this process and then getting deep. I'm not saying it's deep in the sense of really go to the weeds, but also it's by doing this, it's kind of you have your own little neural network running, and then to get all the results.
Yeah, no, I think so. For PhD students, I remember in graduate school, kind of the turning point in my career. You know, as a student, as an undergraduate student, you know, you read the textbooks, you read these theorems and so on, and you know, you're learning mathematics, but it's mathematics that's coming down from the heavens. You know, you get this textbook, here's the textbook proof, and it's, you know, and there's kind of a turning point when then you start to read, you know, recent papers and maybe preprints, and maybe the preprints aren't that great and they're buggy and so on. You start doing mathematics. There's kind of a switch when you realize, I can do this, right? I'm part of the process. That it's you know, it's not that these things emerge fully formed, right? But there's this mathematical process that we're part of. And so I think that's what a mathematical education is all about. It's learning to become part of the process.
That's very interesting, like, perspective, because mathematics, there's also like a social, like, property over there, right? Because this field needs to decide like a kind of a consensus of how you communicate this problem and what are the interesting problems and etc. Right? And I think like the education is kind of part of that, which is like you absorb all these traditions, and then you started to become more capable of understanding all this and to be part of it. And I think this is a very pure form of like participating in this research. And the other part I just connected, which is when I was doing my undergrad, I still do a bit of math stuff. You know, I still can integrate stuff back in the days. But I think I realized that, you know, doing undergrad is kind of like, it's more like a mechanical, like, application of maths. And then when you start to do grad school, at least, I mean, I can only use my grad school experience too, but it's like, now it's more or less like, okay, I got the intuition, and I started to do this creation process.
Yeah, it's the creative. It's like you make stuff up, and you realize, look, I can make stuff up. You know, Gauss made some stuff. You know, I mean, Hilbert made some stuff. You know, that's what you make stuff up. And But then the learning process, and what we try to advise our students is, you know, okay, you can make stuff up, but now how do you make up good stuff, right? It's how do you sort of it's choosing projects and deciding what's valuable.
Right. Again, like I was about to ask you on this questions, like how do you think about teaching proofs and reasoning in an environment where, like, you know, Lean plus LLM scaffold is kind of generally available, and I think you already answered that to some extent.
Yeah. No, I mean, I do think I'm not even sure how we should be teaching calculus going forward. I do think AI should play a role, but probably a small part. For the most part, I think we should probably keep doing the things we've been doing, for the reasons you described. It's just understanding that even though you know, symbolic computations that can do integration by parts and so on, right? Having students do it is a way of understanding the concepts and the meaning and so on.
In the sense, like, education is pretty experiential. People who graduate, they don't need to do integral anymore in their life, but it's kind of like you have to experience that. This is true regardless of agents, right?
But I do think now, but I think going forward also, we will be training our students how to use AI and how to use AI effectively. So I think AI now will become yet another part of the experience that we have to internalize.
That is definitely true, yeah. Great, okay, maybe let's move on to our last topic, this industry trend, and also some of the recent effort you're spearheading. Because I think mathematics, or maybe mathematician, typically people are very enthusiastic about math itself. People have like enjoying their math, but recently there's like huge attention on this like AI and math stuff. A lot of like math talents are moving to industry, like OpenAI, Google. There are newer labs like, you know, Harmonic, Axiom, and then maybe MathInc, right? Do you worry about this, or do you think there's some sort of like mechanism in academia that can change this trajectory?
I don't worry too much. Again, for the most part, I have tremendous you know, optimism and faith in mathematics, in the mathematics community. But I do think short term, you know, there are things to be careful about and worry about. You know, it's interesting. So I described that, you know, before I said that mathematicians really just care about solving problems, and mostly I'm thinking about pure mathematicians, right? But, you know, there's a spectrum from pure to applied. But even on the applied side, people are more interested in just thinking about mathematics than, you know, than making money, or, you know, building, you know, or startups and things like that. And so for the most part, for better or for worse, you know, most of industry mostly ignores pure mathematicians, right? You know, and
should do better.
it's like, well, no, but I mean, in a sense that I think, you know, I think mathematicians like it that way. You know, we prefer, we want to do the things. And you know, now we're in this kind of funny bubble where all of a sudden there is all this interest in you know, startups and big tech in training systems to do mathematics. And people have decided that a good way to train models to do mathematical reasoning is to train them on mathematical research and get them to prove research papers. Right. And so now all of a sudden there is this kind of focus and it's still, I mean, look, you know, I mean, so, you know, so the big tech companies and stuff, they're courting some mathematicians. It's still kind of a small number. I mean, most mathematicians are not being, you know, pursued by startups trying to. I think, in a way, it's nice to be popular. It's nice to feel like all of a sudden people want us. Yeah. I expect that. I expect it's mostly a temporary thing. That, you know, that the labs are going to take advantage of the opportunity now to train their systems to prove, you know, to prove theorems, and when they feel like, I think, you know, once they kind of exhaust that, I think the focus is going to go back to training the systems to do things that are more patently useful or profitable and so on, like, you know, doing the markets or engineering and so on. So I do think it is kind of a weird, kind of funny intermediate. I don't expect it. I may be wrong. But I expect this is just kind of a weird blip in the history of mathematical research. And I think, you know, there will be some tensions and so on. But I expect that in the long run, for the most part, industry will go on to kind of go back to ignoring mathematics, except for the kinds of mathematics, again, that feed into applications and are more patently useful.
Yeah, that also justifies that why you are starting the Institute for like Computer-Aided Reasoning in Mathematics at Carnegie Mellon. So do you want to say a bit about it?
I do. So, this was just launched last September. It's funded by the National Science Foundation. So the National Science Foundation maintains 7 mathematical science research institutes across the country. So one of them, ICERM, is here in Providence, just down the hill. And they're really wonderful resources for the mathematics community. Each of them, you know, various among them have different foci. But a couple of years ago, the NSF was signaling that they saw, you know, AI, you know, on the horizon, and they were concerned about understanding how the mathematics community should be reacting. And so, you know, we proposed the institute really to respond to that challenge. And so the mission is really to help mathematicians navigate the age of AI, learn how to take advantage of all these amazing tools that are out there and use them.
That connects to the education objective as well.
I mean, now it's mostly focusing on educating the mathematics community, I mean, as I said, it's going to involve, you know, collaborations between computer scientists and mathematicians. So in part, it's trying to bring the communities together. But, you know, for the most part, the AI tools are not designed for mathematicians. They're not designed with mathematicians involved. And it's sort of helping mathematicians figure out, you know, what they can do with the tools and help think about how they can use them effectively. So in fact, we just co-sponsored a meeting with Principia Labs, a startup in San Francisco. So we co-sponsored a meeting in San Francisco called Milestones for Autonomous Mathematics Research, which brought together mathematicians and representatives from several labs, both, you know, big tech and startups, to think about what the goals are for AI for mathematics. And in part, there's almost this philosophical side. You know, what does it mean to do mathematics? What does it mean to do mathematics research? Right. And you know, what are the appropriate measures? How will we know when AI is doing something useful? Yeah. And I mean, as you know, AI is very much benchmark driven. And if all the benchmarks are prove this, prove that, we're going to get lots of, you know, neurosymbolic provers. Right. But as I said, there are all these opportunities for AI to really contribute something to mathematics. And so it's the mission of the workshop was to try to articulate, you know, some of those goals. Right. And the work is ongoing. So Elliot Glazer was one of the chief organizers, and he is leading an effort to to write up some of the conclusions and try to share them with the mathematics community and
maybe CS communities
and CS community,
yeah,
right?
We can
to
learn
try
from
to share.
Yeah. I think this is going to be super important because I think there was a recent talk which is like it's a golden age of asking questions. It's kind of crazy that one single person can do so much, but also this is kind of like a trap. If you don't think carefully and then ask the right question, you will waste a lot of time doing stuff. And I think it's, from my view, is like I always love working with experts, domain experts, and I think being able to see like what experts think about and what experts seriously reason about the nature, the essence of this subject with the new AI technology, I think it's kind of like fabulous and then very, very instrumental. And then we love to see that, and maybe we can also share that with our audience.
So just a few weeks ago, the institute directors met. So all the institutes work very closely together, and we're trying to think of ways to make the case for the importance of mathematics in the age of AI. So I pitched a slogan. I came up with a slogan. Okay. So AI may have the answers, but mathematics has the questions.
That's perfect.
Okay, so as mathematicians, it's up to us to figure out what we want to know and what's important, and so.
So I'm just curious, like as of today, in 2026, I don't know, like do you have some thoughts about, like, do you want to make predictions about like, along if we keep this trend, what will AI and math look like in 2, 3, 5 years?
Looking back over my career, there are things I've gotten wrong and there are things I've gotten right. I don't think I have any special powers of prediction. But I think maybe the one thing I have is the humility to know that I really don't know. So again, the thing that I'll repeat, I have tremendous faith in mathematics. I think is the one prediction is I have that the next few years are going to be really, really interesting. That that mathematics, I think, will continue to thrive. That we'll figure out amazing, exciting, interesting things that we can do with the technology. I really don't know what it'll look like. But it'll be great.
So that's the greatest prediction, which is like there's a very high variance, but also the mean is going up. Okay, thank you so much, Jeremy. This is awesome.
Shannon,
I learned a lot from this
It's
talk.
absolutely been a pleasure.
Yeah, thank you so much. Great.